Okay, 7.2 is on permutations. So there's basically two types of counting problems, two big types of counting problems. One's called permutations, which we're doing today, and the other one are called combinations. So the difference between them, well, I'll give you the definition of permutations. Permutation is an arrangement of objects in a definite order. So with a permutation, order matters. For example, when you're unlocking your lock that's used to keep your stuff secure in your locker, you have to go to each number in a definite order, right? Otherwise it doesn't work. So when we're looking at all the different well, we use the word combination, unfortunately. We call it a combination lock, but really your lock is actually a permutation lock. It should be called a permutation lock mathematically because order matters. If you're looking at there's 10 kids and you just want to pick 3 to be on a team. So there's 10 kids sitting there and you say, hey, just pick 3 and that'll make our first team. Order doesn't matter then. So that would be a combination, and that's what we'll do next day. So the really important thing when you're trying to figure out whether it's a permutation or combination is remembering permutation order, or if you want, permutation position matters. Okay, so you have your memory device there of the P and the P. All right, there's different types of permutation questions. So one type is when you want to know the number of permutations, like the number of different arrangements of n distinct objects. And we've actually done this. Before I give you the formula, you'll see that you know how to do this. For example, let's say there was 10 different books, and we want to know how many ways can you arrange those books on a shelf. So notice that order matters, because I'm not just saying how many ways can I pick out 10 books or pick out 4 of the books. I'm saying how many ways can we arrange them on a shelf. And when you're arranging something on a shelf, the order matters, right? One of the books could be on the far left, on the far right, in the middle, and those are all going to be different orientations. So in the first spot, if you think of it, you're going to have 10 spots on the shelf. I'm not going to draw them all, but how many books could go in the first spot? 10. How many left for the second spot? 9. The next spot? 8. Next one? 7, 6, 5. What do we do with all those numbers? We multiply. So you would go 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. Once you got down to the last spot, there'd only be one book left to choose from. What's a much faster way of writing this? That's the same as 10 factorial, just like we did last day. And that is actually the formula for the number of permutations of n distinct objects. It's n factorial. And 10 factorial, your calculator, if it's a scientific calculator, should have a factorial button. And if you throw it in your calculator, you will get 3,628,800. I want to impress upon you just how large these numbers get very, very quickly. Yeah, if you want to arrange 10 books and on a shelf, you could do it in over 3.5 million different ways. It's incredible. Okay, determine the number of permutations of 5 candidates' names on a ballot. So you could either think of it, well, in the first spot there could be 5 and then 4, or you just think, oh, it's a permutation. It tells us right there it's a permutation. I'm picking all of them, so it's 5 factorial. Go to your calculator and plug that in, you get 120. Okay, the second type of permutation question is when these objects, like in these questions here, the books question, all the books are different, right? Now we're going to look at situations where some of the objects are exactly the same. So here's another books question, 10 books again. These books were all different. This is my personal book collection. I think you'll see why when you see the books. 3 Math 9 textbooks, so those are all the same. They're identical Math 9 textbooks. 5 Pre-Calculus 10 textbooks, 1 romance novel, and then 1 cookbook. Yeah, that's exactly what is beside me on the shelf right here. No. How many ways can we arrange those books on a shelf? Well, it won't just be n factorial anymore. Part of the formula will be n factorial. Do you think you'd have more or less options if you did it this way? There'd be less because you have all these identical ones which you would have to take into account. So it ends up what you do is you divide by a factorial, b factorial, c factorial, ... where a and b and c is the number of objects that are alike. So I'll just read the whole thing here. The number of permutations of n objects, if a objects are alike, another b objects are alike, and another c objects are alike, is n factorial divided by a factorial, b factorial, c factorial, ... where a plus b plus c equals n. In other words, all these together equal that one up there. This formula actually works for what we did up here. So for example, if you look at the 5 candidates here, it would be 5 factorial. They're all different. So there'd be one of the first type of candidate, one of the second type of candidate, one of the third type, one of the fourth type, one of the fifth type. 1 factorial is 1. All those are just 1. Nothing changes. That probably doesn't help you. It probably confuses you. So let's give you the example. It probably will help you here. There's 10 books, so we want to arrange them on a shelf. So it would be 10 factorial if they were all different. But some of the books are the same as each other. We have these 3 Math 9 textbooks, so we have 3 factorial for those ones which are the same. We have 5 Pre-Calculus 10 books, so 5 factorial. We have 1 romance novel, 1 factorial, and 1 cookbook, 1 factorial. Now, if we've done it right, all the numbers on the bottom should add up to the top. 8, 9, yes, it worked. Another thing you'll notice is the 1 factorials don't do anything. 1 factorial equals 1. So really all we have is 10 factorial over 3 factorial, 5 factorial. You could use it in a calculator. Let's see if we can, how much we can do without a calculator. 10 times 9 times 8 times 7 times 6 times, the rest would be 5 factorial, all over 3 times 2 times 1, don't need to put the 1, because anything times 1 stays the same, times 5 factorial. This is gone, this is gone. Hey, 3 and 2 makes 6, so all we have to do is multiply 10 times 9 times 8 times 7. Don't think I can do that in my head. That is 720 times 7. It's just over 5,000. It's 5,040. Okay, I admit I looked at my answer key, but there you go. It's 5,040. Let's do one more of those type. Oh, 2 more of those type. A lacrosse team's record over a season was 15 wins, 4 losses, and 2 ties. In how many orders could this record have occurred? Well, first of all, how many games did they play? 15, 4, 2, 21 games. So you have 21 different objects to order. So on the top, we're going to have 21 factorial. But some of them are the same. 15 are identical. Win's a win's a win. They're all identical. So 15 factorial. Losses, we got 4 of those. Ties, we got 2 of those. Bottom equals the top, right? Yep, 15 plus 4 plus 2 is 21. Okay, this time let's just use our calculator to figure out the answer. So you take 21 factorial, put that in your calculator, and then what I would probably do is divide by 15 factorial, get that answer, divide by 4 factorial, get that answer, divide by 2 factorial. Or you could use brackets and stuff. I find sometimes the calculator just seems to get overwhelmed or something. I sometimes have troubles with it. Anyway, I would pick up my calculator if I were you and try it out, see if you can get the answer right there. 813,960 different orders for that record. Now, what if you knew that the team started the season with 5 straight wins? So they end up with a record like this again. This is their final record, but you know they started with 5 straight wins. Well, if they started with 5 straight wins, what are we left with? We're now left with 10 wins to go, and they still have to get their 4 losses and their 2 ties. So how many different things are there to order now? Now we're down to 16 things to order, 16 games to order, because the first 5 are taken care of. They were all wins. So to order 16 things, it would be 16 factorial, but this time we have 10 wins, which are the same, 4 losses, which are the same, 2 ties, which are the same. If you throw that into your calculator, you will get 120,120. Nice number. Okay, the last type of question. What if you don't take all of them? Like again, remember our question with the books, the 10 books? Well, here's the question. What if there's still 10 books? This time they're all different again, just like the first question we did back here. Right? There's 10 different books, but this time instead of arranging all 10 on a shelf, we're going to arrange some of them on a shelf. We're going to only arrange 4 of them on a shelf. How do you do that sort of question? Well, first of all, there's a couple different ways you show this. You could, if you were talking about the number of permutations of n distinct objects, so n different objects, and you're taking r of them at a time. The way you write that is n p r, kind of like National Public Radio in the United States. Or you can write that as permutation of nr, like that. And what it equals, like the actual formula you're going to use, is n factorial again, but this time it's n take away r factorial on the bottom. That's what you're going to divide by this time. Okay? So there's 10 different books, and we're going to, there's 10 different books total. So if we were going to order them all, it would be 10 factorial. But we're not ordering them all. We're only going to order 4 of them. So your r value is 4. So what you end up in the bottom is 10 minus 4 factorial. In other words, 10 P4, or the permutation of 10 objects where you're arranging 4 of them, equals this. Let's do this one without a calculator. That equals 10 times 9 times 8 times 7 times 6 factorial. 10 minus 4 is 6 factorial. You can cross out these. You're left with 10 times 9 times 8 times 7. That's 720 times 7. Didn't we already get that number we did before? We did. It's 5040 again. Okay, the last one. A popular rock group has written 30 songs from which it selects to perform at a concert. How many different opening sequences of 3 songs can be performed? So they're backstage and they're arguing over which songs of our 30 we have to choose from. What should be our first 3 songs? Because we want to really hit the audience strong, right, at the start. We're going to come out all guns a-blazing. How many? So they've got 30 to pick from, and they're picking only 3 of them. So how many different, I mean, they're back there arguing. They're not starting until they look at all the different alternatives to see what would be the best. Let's see how long it would take them to look it over. So on the top, you would have 30 factorial. On the bottom, you would have 30 minus 3 factorial. So that equals 30 times 29 times 28 times 27 factorial, all over 27 factorial. These cross out. You need to multiply 30 times 29 times 28. And if you do that, you get 24,360. These people, this rock band, had better get going. They have to go through 24,360 different possibilities before they can decide on which one would be the optimal one to start their concert with. The audience may be a little impatient by the time they get to it. Okay, that is permutations. Remember, permutations, order matters. Order matters. It won't be so difficult today because all the questions are permutations. But once we get to permutations and combinations, you're going to have to keep reminding yourself and asking that question. Does order matter? For permutation, order always matters. This is the code.